Good everyone, my name is Graphics. Today we want to study an aspect of thermodynamics which is called refrigeration cycle. Now, if you look at the word refrigeration cycle, this is a thermodynamic cycle that is designed to provide cooling or heating, right? The word refrigeration cycle. When you say cycle simply means when a system goes series of processes. So it means that in a refrigeration cycle we have series of processes for which to attain cooling or heating. We should know in our mind or from our past knowledge that we have two statements of the second law of thermodynamics. And these two statements, one of them is the Kelvin-Planck statement and the other is called the Clausius statement. Now when we talk about the Kelvin-Planck statement, we are talking majorly on heat engine, right? We'll talk about the Clausius statement, we're talking about the reverse heat engine. So from this reverse heat engine, that is what brings about refrigeration cycle, because the reverse heat engine have two consequences. The first consequence of the reverse heat engine is your refrigerator, and the second consequence of the reverse heat engine is what? Is the heat pump, right? So the refrigerator on its own is a reverse heat engine that is used to remove heat from a region and maintain that region at a temperature lower than that of its surrounding. Are you with me now? So that brings about what? Cooling. Why the heat pump tends to what? Concentrate heat to a region, right? And leave the temperature of that region higher relative to what? Its surrounding. Now, one thing you need to know is that we want to analyze the refrigeration cycle, and we'll be considering few refrigeration cycle that is in common use as a case study, right? So one of these type of refrigeration cycle we'll be using here will be the CARNOT refrigeration cycle. The CARNOT refrigeration cycle, the CARNOT on its own, the CARNOT cycle is used as a theoretical standard of comparison for all power cycle. That is the CARNOT cycle on its own. So we use it as a standard for all power cycle. Now, what about the CARNOT refrigeration cycle? Now, the CARNOT refrigeration cycle gives the maximum possible value of the coefficient of performance for given temperature limits. At low temperature, when I mean temperature limit, I mean between high temperature limit and low temperature limit. For the high temperature limit, we are talking about the temperature of the working fluid, which is refrigerant, at the condenser. When we talk about the low temperature limit, we're talking about the temperature at the what? The evaporator. As we move further, we are going to understand this. So let's move forward. So these are the summary of what I explained earlier. Right? Yeah, the summary of what I explained earlier. Now what we're looking at will be the diagrammatical representation of a CARNOT refrigeration cycle. But one thing you need to understand that in a refrigeration cycle or in a refrigerator, we have 4 components, right? And the components that we have are the compressor, the condenser, the expander, and the evaporator. So that is what we have. So look at the diagrammatic representation of a CARNOT refrigeration cycle. Now this is the diagram here, and this guy here is representing the compressor, right? And this guy here representing the condenser, and this representing the expander, and this is representing the evaporator. So these are the 4 components. Just like we have 4 components here, we also have 4 processes that this cycle undergo. So we go to the processes. One of the processes is called isentropic compression process that occurs in the compressor. So that's the first process. The first process is called the isentropic compression process. So when you say isentropic, it means the word is a reversible adiabatic process. Like I said earlier, it occurs in the compressor, right? So as I am explaining this, I'll be using a TS diagram to analyze the movement of my refrigerant. So my TS diagram, I'll be placing it here. So this is my TS diagram. Here will be T, and here will be X. X is standing from entropy, T is for temperature. And I'm going to draw my dome-like shape this way. Now, one thing you need to understand here is that if I divide this into 2 this way, right, everything on my right is a gas, everything on my left is a liquid. So I'm using F to represent that. So everything within here is wet, so we usually call it FG. How good? And this line is called my saturation line. This line you're seeing here. So at the left hand side, from here downward, is called my saturation liquid line. From this point to this point is called my saturation vapor line. So whatever touches this line is what you can see in your steam table. Whatever is outside the line or inside the line is what you are going to calculate for. So now I want to use this line to analyze my my CARNOT refrigeration cycle. Now we say the first stage here, stage 1, we'll call it isentropic compression process. I said the word isentropic means there's no heat input or output into the system. So at the compressor, there's no heat input or output into the system, right? So at this state here, this state, I'll call it my state 1. The state 1, let me draw my CARNOT circle here like this, touching here, coming down here, and coming down here. This is what I have to represent my CARNOT circle. So we have 1, we have 2, we have 3, and we have 4, and it is going this direction, right? It's going this direction. It's going anti-clockwise. So at this state 1 here is this one here. Now what do you notice? At state 1 here, it is falling into this region. So it means that at state 1, it is still, there's still some kind of liquid, because at this place our dryness fraction is 1. At this place our dryness fraction is equal to what? 0. So everything here is liquid, everything here is gas. But when it is very close to it, that means there is more gas than what? Than liquid, right? So At this point now, this state 1, there is more gas than liquid, so it's something like a wet vapor. So there's more gas than liquid at this state here. So at state 1, the temperature of the refrigerant is the working fluid. The working fluid there is the refrigerant, which is the system. As it moves, state 1 is the entry of the compressor. So the liquid, the gas at low temperature and pressure, enters into the compressor, but it still has some liquid, right? Not a complete gas. Now, as it enters here, the compressor compresses it adiabatically without its input or output into the system. So what happened? It moved to what? State 2. State 2 is the exit of the compressor, right? So it moved to state 2. So at this state now, what do you notice? The temperature is high. At state 1, the temperature is what? Low, right? So it increases the temperature from state 1 to state 2, and also increases the pressure too, because when you compress, you are indirectly increasing the pressure. Now that is for state 1. So at state 1, things you need to understand is that at state 1, the entropy at state 1 is equal to what? The entropy at state 2, right? And also we know that what? Our Q from state 1 to 2 is equal to what? 0. Because of what? It is adiabatic, right? And the pressure is high. Now what's happening? The compressor is doing work. For it to compress the fluid, the refrigerant, it is what? It is working. So we call it work input, W12. Is that okay? So we're compressing the vapor. That is process 1. For process 2, we call it condensation. At process 2, we call it what? Condensation process. Condensation process. So at this state now, the state 2, which is the exit of the compressor, is the entry of the what? Condenser, right? So liquid at this point now, it is a pure gas, because what is happening, it is touching this shape, the dome-like shape here. So it means that what? Dryness fraction is 1. So that means we're all talking about gas. So when it has entered the compressor and comes out, it is now pure gas. But the gas here now, we'll call it dry gas. So as the gas is here at high temperature TH, it enters into the condenser, right? So at the condenser, what does the condenser do? It tends to turn gas to what? Liquid. By what? By lowering the what? Temperature. Trying to lower the temperature. Is that good now? So, but in this case, when it enters from state 2 coming to state 3, at state 3 it becomes what? A fluid, because it has come to this point here. So it becomes a fluid at high temperature, right? But the pressure remains intact because we have the same pressure. Now, one thing you need to understand the condensation process again is that what? The liquid is saturated. The liquid is what? Saturated, because it's touching the saturated liquid line. The gas here is saturated because it's touching the saturated vapor line. Now one thing you need to understand is that what? The temperature here, T3 at state 3 is equal to what? Temperature at what? At state 2. T3 is equal to T2. Right? So now we also need to understand that the entropy at state 3 is equal to what? The entropy at state 4. Now let's move forward. Now the next one, we talk about condensation. It turns the gas to liquid, whereby there is heat rejection at the condenser. Because when the gas is losing temperature, it comes to what? Turns to a liquid. Now number 3, we're talking about isentropic expansion. So isentropic expansion occurs at the expander. Isentropic expansion process occurs at where? At the expander. This is the expander here. Now, when the liquid at high temperature moves, it enters the expander where it is expanded isentropically without the help of its input or output to state 4. Are we good? So I want you to understand is that what? Q3 to 4 is equal to 0. So at the expander, no its input or output. At the compressor, no its input or output. At the expander, the entropy at the entry of the expander is equal to what? The entropy at the exit of the expander. The entry of the expander is state 3. The exit is what? Is state 4. Right? Now it will now move back to its original low pressure. Initially at state 1 the pressure is low. At here also pressure will be low and temperature also will be low, because if you look at this graph here, T4 is low. So it moves from high temperature to what? To low temperature. Right? So, and again it still falls in between here, but it's closer to this shape here, this dome like shape. So it means that what? As it's closer to this point, we have more liquid than gas. Here we have more gas than liquid. We have more liquid than gas at state 4. So then the last one here that we have is called the what? The evaporation process. The evaporation process, state 4. We have the evaporation process. So we know the work of an evaporator is to evaporate, right? Is to what? Increase the temperature of a fluid, right? So when the liquid at state 4 enters into the evaporator, then it's absorb heat. So at the evaporator there is a heat input. The heat is absorbed. So at Q4 to 1 there's heat absorbed, right? So as it enters here, it starts boiling. As it's boiling, it starts evaporating at low temperature and pressure to state 1. So at the evaporator there's heat added. At the condenser, heat is what? Rejected. So I use Q2 to 3, heat is what? Rejected. Q4 to 1, heat is added. But at the expander, work is what? Is done to the surroundings. So we have W3 to 4. So from W means from state 3 to state 4, we're having that. You can see that. So that is the evaporation process. So those are the 4 processes that occurs in a refrigeration Carnot refrigeration cycle, right? So know that state 1 is the entry of the compressor, which is also the exit of the evaporator. State 2 is the exit of the compressor, which is also the entry of the condenser. State 3 is the exit of the condenser, which is also the entry of the expander. State 4 is the exit of the expander, which is also the entry of the evaporator. So the next we're talking about will be the coefficient of performance of what? A refrigeration cycle. These are the analysis of a Carnot refrigeration cycle, and I said earlier that it is just the basic for other power cycle, and we've gone through the processes. So if you found this video helpful, don't forget to like, share with friends and family, and don't forget to also click on the subscribe button. Thanks for watching.